Okay, so I'm very excited to hear Dave Neuffer's discussion of how we move forward in either, both, and intensity and energy.
Hopefully both, but we never know. Okay, yeah. So thank you for the introduction, and actually thank you to GTI for the invitation to be here. I've had some very interesting discussions uh, during my time here. It's been very enjoyable. Uh, and I also want to thank Larry and Vladimir for their presentations because they basically convinced me that we should build a muon collider. Frankly, I've been very skeptical, but who knows? We shall see. I mean, the overview here is kind of, and again, I'm starting from the Fermilab perspective where we go to the glory days of Fermilab, the Tevatron, where we were the energy frontier and we upgraded it in intensity. So we were doing intensity in the energy frontier, which CERN with LHC was able to do the next energy step. So we're now envious that the energy frontier is not at Fermilab, but of course we help participate in that wherever we can. We uh, and for Fermilab, this changed to an emphasis on an intensity frontier. That roughly if I have the dates right, 2014, the P5 says, well, within the U.S. resources, which are basically at that time, no project over $1 billion could be even proposed, and anything at the energy frontier would be much more than that, and they thought perhaps mistakenly that the intensity frontier was more affordable. So that's what Fermilab's focus was at that time. And so I'll go into a discussion of that, and from there discuss where the currently the intensity frontiers are, and then where the energy frontiers might be. So here we are at Fermilab today, where we are an intensity frontier facility, where we have the nominal intensity accelerators are the booster, which has been and its current status can actually run up to about 100 kilowatts. We haven't run it at that intensity. We've done maybe 20 kilowatts to stuff like the neutrino beams, but we now have that capability with the upgrades to boost the booster and the main injector. We now can run up to 1 megawatt of beam on target currently for the neutrino beams, neutrinos line. And so that's giving us an intensity frontier program, and we also have a muon beam program, which is also at the intensity frontier. And again, this sort of we have a muon beam line that goes to both the G-2 experiment and then to the MUDI-E experiment while this is being commissioned. And it's had an enormous success in the G-2 experiment. We've measured the G-2 with a higher intensity beam, 10 to the 12 odd, using roughly 10 to the 12 odd high energy muons. And as a result, the G-2 anomaly has been resolved. Not because we changed the measurement, but somehow the theory decided to agree with the experiment, or was able to. And actually, I think this is maybe a real triumph in lattice QCD calculation. Oh, okay, yeah, you may have a different view with more knowledge of what's going on in the calculation side there. Yeah. Okay. Good. And so we're now initiating the MUDI-E experiment, which is significantly higher intensity, at least the number of muons. And the other thing about this is it is sort of a micro model of what we are will be doing for the muon collider if we do it. And since I've been convinced by yesterday's speakers we should be doing it, I changed costume for that reason. Okay, it's sort of proton beam in a capture solenoid, which is our current baseline for how we're going to capture muons for the highest intensity we can get for a muon collider, um, and then transports them along a solenoid system and stop them. Uh, and well, actually stopping them as target is a form of cooling. And we're actually getting something like, well, the plan is we haven't fully commissioned it, getting around 10 to the minus 3 muons per proton. That's actually not that different from what we hope to get for a muon collider. By the time we cool and accelerate the muons, we're actually less than 10 to the minus 2 muons per initial proton. So, and we could actually in this geometry we could probably do that by going from backward to forward capture. However, the any rate, so this and again, this will be using at least 10 to the 18th muons. This isn't quite a millimole, but it's a micromole or several micromoles. So we're getting there. to and again, as part of our intensity upgrade program, we're building a higher intensity, higher energy LINAC, which will give us actually a very high intensity megawatt at it, potentially at the initially 800 MeV, but really GeV scale. And with that, we can with that upgrade, we can then increase the booster to 200 kilowatts uh, and go to greater than 2 megawatts for the future neutrino program. Um, so this is all, again, a really intensity upgrade, and this is sort of the uh, details of that, and as this is being developed and using our frequencies from starting at 162.5 to 650. You could add a 1300 megahertz LINAC to the end of that. That was maybe a future plan. Uh, but these are, you will also recognize these as kind of the frequencies we want to use for a future muon collider, and we sort of cover what we need for the cooling system maybe and capture system. Again, not quite the same, not really the same cavities with this developing that technology. And again, with PIP2, we have new, particularly with the megawatt semi-CW mode, where actually the neutrino program is only using a fraction of it. So we've, again, discussed, and maybe in the future we'll have more ideas on that, how we could use this for lower energy beams for various intensity frontier experiments. Our first one is MUDE, but maybe we'll have others, and we could do other things which aren't really considered high energy physics, nuclear physics, with pions and muons and mu. Well, we actually the U.S. doesn't have a mu spin rotation facility, and we could use one. And eventually we'll, again, going on the intensity frontier mode, uh, um, consider replacing the booster with something higher intensity, maybe higher energy too, but something that could take us to another level of frontier on the intensity frontier. And uh, the Fermilab baseline physics program, then, or at least the flagship thing, will be the neutrino physics as Dune, which will get us, as I guess Luca described last week, uh, uh, hopefully a more complete, accurate picture of the three neutrino model, and maybe and again there'll be other physics in that program. Although I know the continuing MUTE program is a possibility, but the other possibilities are something we would like people to develop. And again, well, here I'm just sort of saying, or we started thinking about how we might upgrade the booster to something higher intensity that now would be 2 megawatts at 8 JeV. And of course, maybe another factor two at a more broader range of energies from the main injector. Uh, and so we're sitting here at the intensity frontier. LHC at CERN, they're also looking at what they should do on the energy frontier or intensity frontier or both. And they currently have they do have the energy frontier, and their first step is intensity upgrade. Improve the intensity, get another order of magnitude in data, and 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 again, as look at, I think, well, this is what last week was described that would roughly a billion-dollar scale project, but gets them to the next level. Another, they are considering a Higgs factory, which would be turning super large, the 100-kilometer ring running E plus E minus. That I would consider intensity frontier. We've already passed that energy level at the energy frontier at LHC, but this would be an I consider that an intensity frontier experiment. But it has some important physics that we'll be able to do. However, both the European strategy and now the U.S. system is now also thinking of the energy frontier, and that has led Europe to reconsider a muon collider um, as a way that to for an energy frontier facility. They are also considering trying to use the 100-kilometer ring for a proton collider. Of course, we would want to do both. But at any rate, so they've developed the muon collider scenario from what we were able to do in the muon accelerator program. That was that was deferred in 2015 odd. And so I'm just sort of writing down their vision for what they might be able to produce in the future. They've worked that out in more detail in this is a CERN. Well, they've looked at a greenfield implementation, but also looked at it at CERN, and it makes actually relatively minor changes to the CERN footprint. They plan to could use the LHC as the accelerator tunnel, so the amount of actual civil construction is, well, relatively small for a super high energy project. Fermi, and in part because of their improvements, we're also started to think, well, gee, we could do this now. We really could, maybe, and even fit it in a similar size footprint at Fermilab. Again, maybe here we tried to keep the accelerator ring within the Fermilab side, but that we could imagine extending that beyond. Our congressman has encouraged us to consider that, but at least and to be honest, it's kind of stretching it to get a TV collider and the accelerator at current technology on the Fermilab side, but a little bit over, you'd be comfortable, or maybe with technology improvement a bit. So here we are, but as the Muon Collider collaboration has noted, we have ideas on how to do this, but we haven't built very much of what we would need to actually do that. And so both, well, really initiated by the initial International Muon Collider collaboration, they've started to look at what they need to build to demonstrate we could actually build this in detail. And so the focus has been, can we do ionization cooling uh, in an actual hardware system that we can run? And that's kind of important. And at some level, it's also a model for everything else we need here. Because basically, to do that, we've got to demonstrate we can do uh, medium high gradient RF with competing magnetic fields and integrated with high field magnets and um, and RF and and eventually uh, beam from uh, a produced muon beam. So with the thought that, well, if we can do that, we can probably do a lot of the other stuff we would need to do. Uh, so working that, and so this is, I'm going back to here where we now have something in the current program where we're getting up to a 2 megawatt proton beam, and we could even go greater than that again with the 10 GV thing. And I'm not. I'll give this in here. Actually, there's you could actually consider using the upgraded main injector with higher intensity as the driver rather than a booster replacement, but I won't. That's an exercise for someone to work out how well that would work. But it's could actually be considered at least a start point. But now we're at a point where, oh my gosh, we've got something we could drive a muon collider with, just by coincidence, and maybe we can do it. And so this has led to, well, late P5 report, which is even more ambitious than I've ever been. That's the first recommendation. We should build a muon collider research facility and and then enable construction of such a thing. I don't know that. So, however, we really haven't done anything on the U.S. on that yet. So that's one of our problems. Um, and I've copied here Daniel Schulte from the IMCC, his vision for how one could do a muon collider in the future. And again, he puts in a timeline here where you even have a running accelerator before 2050. But that's certainly possible. It's again driven by whether we can do that. You can do an R&D program that convinces that you can build it, and then go on to build it. It's as Daniel noted here, there's a hesitation here. This could be the next flagship after the high lumi LHC, but uh, he's aware there's a bias toward going for FCC first before we go to the energy frontier. And if one did that, you could still do this, but on perhaps a longer timeline in Europe after the Higgs factory, or as he noted, but I wasn't going to say it on my own, in the U.S. Because they've really done a lot in advancing the idea over the last few years. And this is sort of, again, this at this time thing, it's very bureaucratic, but if you look in the details, there's lots of the various hardware things you're going to have to build and test or at some level, again, at least when in terms of cooling, trying to get demonstrate you can actually run this complex RF plus absorbers plus uh, plus magnet focusing system and get significant cooling. And I've sort of put the cooling Linux here. And I'm also, well, I have a intuition that in the R&D we could, there's another invention or improvement in the general cooling system that can be done that will turn this from something we're thinking about doing to something we've got to do because it's just obvious. So I'm leaving us to learn how to improve in this system. any rate, so and again, this is copying from the CERN thing that they said, oh, gee, well, these are the various magnets we'll need. This is the kind of R&D we need to get them. I guess there's a high field capture solenoid, which we would use, but there also could be used for other experiments. Uh, and and let's see, cooling magnets. The hardware for that is, of course, a bit more complicated than the initial simulations. Um, and, and at any rate, these are sort of the suite of magnets you need to develop to actually build a whole facility. And in the U.S., we maybe will try to catch up on it. We are forming a U.S. muon collider collaboration, and again we have a timeline here. This is from the last collaboration meeting where our year zero is still we're still at year zero, but we plan to hopefully be able to move on to year one next year, but we'll see. But actually, basically, if you, in outline, it's kind of the same thing as the CERN thing. The important thing is to try to get R&D from both in Europe and the U.S. and complement it so that we do pieces that they're not doing, and we help each other on the various pieces. That's the ideal. And so that would be sort of, I guess, sort of would lead us into a program and through the 2030s. Uh, if, if one, and at any rate, this is kind of this really, if you look at it, and again in detail, a little different, but uh, same sort of roadmap and what ideas and what we need to do to get to where we can say, gee, we know how to build each piece of this, and we've got it, and we can get pieces of it to run, which actually has been our difficulty in previous experiments. We've had yeah, but at any rate, but demonstrating that we can actually build things that that we've put on paper would be helpful. And this is, again, the U.S. look at some of the things we would need to do, certainly the RF studies in magnetic field, and kind of looking at different RF configurations we might consider both for the cooling and also, I haven't put it in here, but the acceleration system has very uh, interesting RF requirements. And again, build a cell, and then at some point it would be a good idea for us to perhaps build a different part of the cooling scenario than what CERN is, and complement the two programs. So, and again, sort of an idea, well, we can also build a proton, we could take advantage of the high intensity proton source we already have at Fermilab and will have in the future, and build a demonstration facility here. And with that, we took, at any rate, so this CERN is advanced on what their demonstrator is. They're sort of currently thinking more specifically of, say, a cooling cell that in simulation or our lowest level uh, mode looks like this, but when you try to put it into more significant hardware with physical RF cavities and RF inputs and coils with cryostats, looks a little more like this. I think they've done more detailed than that, but that's sort of the idea of what we would need to do. And if we, and again, I've sort of, and this will be a topic of R&D at firm in the U.S. Muon Collider collaboration. What kind of demo could we do at Fermilab? I'm sort of thinking, Scott and other people said, be nice to do kind of a scaled back version of front end where you have, say, a 5 Tesla capture solenoid rather than a 20 Tesla one. This is actually just the same roughly the same parameters as the Mute solenoid, and then some sort of capture and drift to develop a muon beam, which then could go into something that tests cooling devices. I put in here sort of our initial look at what one of the highest field cooling cells might look like. We might do those, or also something earlier in the scenario. It would be also nice if this could be something that could be used as a physics device, say for well, as he noted, if we I think we could consider maybe generating a pi or mu decayed neutrino beam from this. If this could you could, well, in principle, this could take like 10 to the minus 3 muons per proton, um, and and multi-kilowatts of protons from primary beams available at Fermilab. So that's a possibility. And actually, I hope the collaboration will come up with even better possibilities. So this sort of is where we are now. It's thinking, well, what's the next step? And well, we'll have well, next step is there's a muon collaboration meeting uh, at based at the University of Chicago. I guess that's next week. Oh wow, a lot sooner than we think. But probably really to start the discussion, to get something more specific. Again, we're hoping that we're hoping that Fermilab will assist in that as well. And so again, I'll sort of leave that for us, rest of you to develop in the future, hopefully.
Okay, thank you. Who has questions about this whole scheme to get us to
Who has answers?
or answers? Yes. Who has thoughts?
Yeah.
A question about, if you go back a slide
Yeah.
to the Fermilab demo idea. Yeah. So you mentioned that the capture solenoid would be similar to Mu-to-E's capture solenoid.
Yeah.
Um, is this a proposal for reusing that setup?
I discussed that in the last meeting. The problem is it's set up to take backward muons,
Right.
which are lower energy. It's yeah, you'd have to. I mean, in principle, you could take their exact solenoid and redo the beam line and take forward muons, but Mu-to-E doesn't
So yeah,
want
that
to
was
do
going to be
that.
my next question. When is the end of Mu-to-E? Right, right, exactly. Yeah,
Yeah,
that's fair. Yeah, okay, I see.
yeah.
I
So
see.
at some level, and another thing to think about is their experience with their high field solenoid has been more difficult
Okay.
than well. Uh, I think they had a problem with well, anyway, the contractor did not deliver on time and on quality.
I guess a related question then for this sketch, if the idea is to go, low power, low numbers, this kind of thing.
Well, compared to the full meal.
Yeah, exactly.
But compared to what we have now, it could be a couple of orders
Right.
of magnitude more.
What of this sketch is particularly hard and or expensive? Or is it all
Oh,
of it?
well, to be honest, anything's expensive. What's hard? I mean, at some level, the fields aren't hard, but we've done magnets with that field and that intensity, and sometimes they've had no problems being constructed and built, and sometimes we've had problems.
Interesting. How
So,
much, like, compared to their cost, which Obviously, we all know that like a big picture of something that looks like a cooling channel sells itself well as a demonstrator, right?
Yeah,
But if you were to try to design something that was as cheap as possible that demonstrated all of the principles you thought were necessary to demonstrate, what would you focus on in a demo?
yeah, I probably focus more on individual
Right.
components than on a string test.
Do you think that there's something meaningful about putting a beam in it in terms of proving something to ourselves? Like actually.
That's a good question. I don't have a full answer to that. Yeah, I mean, there are some things where, well, you could do it with other test beams, but we have some concerns about, suppose we have a beam going through the RF cavity with magnetic fields in the same place. If we're doing a full cooling demo, we'll have a definitive answer on that. If we don't, we can try to test out the situation with smaller scale test beams. But
Mhm.
it's a thing. How much do you spend on a demonstrator? How much do you spend on actually building the real thing?
Mhm.
And and if you, of course, go to building the real thing before you've done enough demonstration, maybe you'll have to rebuild the real thing before you're ready. So yeah, yeah. Uh, okay. Okay, go
So
ahead.
an idea I've heard tossed around potentially for the demonstrator is that if you want to demonstrate like later stages quickly, you can't, you would need like a pre-cooled muon beam to do that. So you couldn't
Not really.
necessarily.
Again, it depends on what you want to demonstrate. I mean, for instance, you produce a cool beam by collimation, then it's much lower intensity.
Well,
But then you can do the basic measurements with that.
the idea I've heard tossed around was that there are some components that you could test with a proton beam, even though the way it interacts with
Oh,
matter is
yeah,
very
that's
different. I don't
kind
know if
of
you have any
what,
thoughts on that.
if our worry is, oh, a beam going through the system may cause breakdown. We can use a proton beam as kind of a model for a muon beam. And yeah, actually sort of, at least it's different, but it's the basic problem, does beam through trigger breakdown? You can test with a proton beam, and since you can run proton beams at higher intensities, you may be able to set higher thresholds than what you could do with a muon beam test in terms of beam intensity going through. Because of course, our first demos with a muon beam will be nowhere near the intensity of what we would want to get in the final collider. So you could say, well, run higher intensity proton beam through and see what happens. I mean, you may get things happen, but some things will happen with protons that wouldn't happen with muons, which, and you have to distinguish, that that whatever uh, some problems would occur with protons that wouldn't happen with a real muon beam.
Someone said the other day that we need not to test or establish principles, but implementation. And I totally agree with that.
Yeah.
A jaundiced view of the mice experiment is that it did nothing. You may want to respond to that. Because all the answers are in beta block or classical electrodynamics and so on. And so we really, I mean, you're going to be asking for billions of dollars to do this.
Right.
You better be sure that it's not just a sketchy implementation of something that you show, but that you really demonstrate that we can make beams of the quality we will need in order to capture them, accelerate them, eventually bring them into collision.
Yeah.
And that means that these things are not going to be done on the cheap. In the US, our problem has been inconstancy of the agency, inconstancy of lab directors. Lab directors are different from the rest of us because they have mouths to feed, and so that warps their perception of how they can spend things. And to be fair, they've had much less autonomy in the last 15 or 20 years than they had before when they were
Yeah,
little
that's a
little
problem.
people who could rule the world. Uh, we have changes of leadership at CERN already named. We will have a change of leadership, or at least a transition of leadership at Fermilab. I don't know what's happening there. And it's very important that those people understand that the muon collider and the research toward it, while not the thing that they must accomplish to pursue their laboratory program, is very important to the future of the field in competition with other ideas that
Yeah.
will be presented to them.
Yeah.
So, yeah, don't try to put a ridiculous upper limit on the cost of a demonstrator. Make it actually demonstrate something that will give confidence to the citizens of the universe that we might be able to do this.
Yeah, and that's one of the things you wonder if you're doing a string test, and when you really just want to know, can you build a unit of it? And building n equals 1 is a little hard, but once you've demonstrated that, building 2 through 5 is not quite as important. Yeah, yeah, it's yeah, there's a balance there, but yeah, you're right. The mice experiment uh, didn't prove anything we didn't think we already knew. Although they did, well, they in terms of hardware, they did build and test a hydrogen absorber, which was non-trivial. What's that? Yeah. Although it's still, yeah. Although I think lithium hydride should be used more in the system because it, yeah, yeah.
I just wanted to say that this is something we might want to discuss on the Thursday discussion. So, but yeah, let me put it in the wrong way. And then you tell me, how should I put it, at this point, I think we've learned pretty well how to not make project happens. Okay, we have, okay, I talk for things I know from a little bit closer in time. I think the experience from ILC that I've been working a little bit on in this kind of physics, not necessarily on the project, click a little bit more. It's telling me that there are a number of ways that along the steps that you have to make to get there to the billions, people will give you hard time asking questions that I will explain at dinner, some Italian joke, how, this is a standard way to, strain your opponent to death. And eventually they will not get anywhere because you put them so many hoops to jump on that they will never get anywhere. And it's true, you have to reason a bit like a lab director, which is a different kind of person, even though the day before it was your friend, now it's a different person. And we have to really reason on how to get the billions in our pocket, because at this point, I believe we have so many good projects, actually. All of them would be nice, but really good, not just nice. And we still fail to get them approved unless you get this big picture 100 kilometers and you realize that there is a lot of sociology that actually pushes it, and maybe less physics than sociology most of the times. So we really have to think hard. I know Tova asked me this, how to do that in Europe, like in Hamburg, and I have no answer yet. I realized that I know many ways of how to fail it. Maybe I can build some antibodies for this, but I think that's really the biggest problem. We don't know how to get these bigger things. Instead, we preoccupy ourselves with how do I get 100 million to this little thing, this mice, a little mice, or hamster, whatever the next is gonna be. That's the biggest problem right now. We don't have the courage to say I need 10 billions for the moonshot, whatever it is. Sorry for blabbing.
No, that's great. It's yeah, we're asking for something humongous, right? It's exciting, but you gotta, you have to have a lot of boldness to make it happen and a lot of savvy.